Chapter 12, Physics Continued. Linear sequential arrays, and then the beam steering section. With linear sequential arrays, a small group of the crystals are fired simultaneously to create each sound beam. The sound beams are parallel to each other and are typically directed straight ahead. For example, the simultaneous firing of the first 10 crystals creates one sound beam. Then another sound beam is created when the next group of 10 crystals is fired. The sound pulses originate from different locations along the face of the probe when different sets of crystals are excited. Beam focusing. In earlier models of linear sequential arrays, beams were focused conventionally with curved active elements, internal focus, or by placing a lens in front of the active elements, or external focus. In this setting, focusing characteristics were fixed and the sonographer could not alter them. In modern linear sequential arrays, focusing is achieved electronically. Modern linear sequential arrays perform both transmit and receive focusing using electronic phase delays. Just like linear phased arrays, electronic transmit focusing is achieved with a curved excitation pattern of the active elements. The outer elements in the group of PZT crystals are fired earlier than the inner elements. Receive focusing is achieved dynamically by introducing electrical delays in the signals returning from the transducer. The phase delays change continuously during reception, thereby focusing the beam at many depths. Image shape. A rectangular image is created with a linear sequential array transducer. The sound beams are emitted from small groups of crystals at different locations along the face of the probe. The image is never wider than the transducer. Although a transducer with a 10 cm footprint may produce an 8 cm wide image, it cannot create an image wider than 10 cm. Damaged PZT. When one element in a linear sequential array is damaged, only the portion of the image extending directly below the damaged element is affected. Recall that only a small subset of the transducer's active elements is fired for each sound pulse. Thus, only the scan lines that would have been created by the defective crystal are affected. More about linear sequential array transducers. While using linear array transducers, why is it necessary to fire a group of crystals to produce a sound beam? Why can't a single crystal be used instead? Recall that sound waves produced by a small active element diverge in a spherical shape or a Huygens wavelet. A sound wave fired from a single element of a linear sequential array would have such a shape. The beam would quickly diverge and result in poor lateral resolution. In contrast, a sound beam created by the combination of wavelets from a small group of active elements is directional and well defined. Can linear sequential array transducers steer sound beams electronically? Yes, linear arrays can steer sound beams electronically. This form of beam steering creates parallelogram shaped images rather than rectangular images. As previously described, beam formers of phased array systems steer sound beams electronically. Sloped pattern phase delays in the electrical excitation spikes of the elements steer the beam. In Figure 12.28, a rectangular grayscale anatomic image is created during color Doppler exams with a linear array. The electrical patterns creating sound beams for the grayscale image have no slope, and the sound beams are directed straight down. However, the color Doppler portion of the image is parallelogram shaped because the electrical spike patterns creating the Doppler sound beams are sloped. Convex curve or curvilinear array transducers. To increase the clinical utility of linear array probes, manufacturers have designed arrays with a bowed or curved shape. These transducers are called convex, curved, or curvilinear. The operational characteristics of convex arrays are similar to those of linear arrays. Crystals, number, and shape. A convex array has 120 to 250 rectangular shaped strips of piezoelectric material arranged side by side in a bowed line. The array is large. The acoustic footprint may be as long as 10 centimeters. Note that the active elements in a convex sequential array are similar in size to a linear array and much larger than those found in a phased array. Each crystal is about one wavelength in width. Beam steering. In convex sequential arrays, some, but not all, of the crystals are fired simultaneously to create each sound beam. The beam is directed straight out of the crystals, but since the crystals are arranged in an arc, the pulses travel in different directions as they radiate out from the transducer. The sound beams transmitted from a convex array, unlike linear sequential arrays, are not parallel to each other. Beam focusing. Focusing in modern convex arrays is achieved electronically, just like linear array probes. Transmit focusing in convex arrays is achieved by exciting the active elements in the fired group with a curved spike line pattern. Dynamic receive focusing is achieved by introducing varying phase delays in the signals returning from the transducer to the ultrasound system during echo reception. Image shaped. Blunted sector-shaped images are created by a convex array. At intermediate depths, these images have a traditional sector shape. However, rather than coming to a point in the near field, the image appears to have a bite taken out of it. The curvature at the top of the image corresponds directly to the arc of the convex array transducer. Convex array transducers create images with a shape of a natural sector. Damaged PZT crystal. When one active element in a convex array is damaged, only the portion of the image directly below the damaged element is affected. Recall that only a small subset of the transducer's active elements is fired for each scan line. Thus, only the scan lines from the defective crystal are affected by its malfunction. Vector arrays. A vector array is a combination of linear sequential and linear phased array technologies. Sloped phase delay patterns can electronically steer the sound beams in different directions. This technology is called vector or virtual sector. Crystals, number, and shape. A vector array is designed with 120 to 250 rectangular shaped strips of piezoelectric material arranged side by side in a line. The footprint of the vector array may be small, often only a few centimeters. Beam steering. Beam steering in a vector arrays combines linear and phased array technologies. Some, but not all, of the crystals are fired simultaneously to create a single sound beam in vector arrays. This is similar to a linear sequential array transducer. The electrical signals from the beam former are delayed in a slope spike line pattern as they excite a group of elements in a vector array. As a result, the beams radiate out in different directions from the phase of the transducer. This is similar to a phased array transducer. Beam focusing. Electronic focusing is used with vector arrays similar to the phased array probes. Both transmit focusing and dynamic receive focusing improve lateral resolution over a great range of depths. Image shape. Trapezoidal images are created by vector array transducers. At intermediate and deep depths, the image appears as a sector. However, unlike phased or convex array images, the top of the vector array's image is flat. Active element malfunction. Transducer type, mechanical. The effect on the image is loss of the entire image. Linear and convex arrays. The effect on the image is dropout of image information from the top to the bottom of the image. The location of the line corresponds to the broken crystal. Phased arrays. Erratic steering and focusing. The extent to which the image is affected is variable. Annular phased arrays. The effect on their image is a horizontal or side-to-side band of dropout at a particular depth. Summary of transducers. Mechanical. The image shape is sector. The steering technique is mechanical. The focusing technique is fixed. Linear sequential. The image shape is rectangular. The steering technique is electronic. The focusing technique is electronic. Phased array. Image shape is sector. Steering technique is electronic. Focusing technique is electronic. Annular phased. Image shape is sector. Steering technique is mechanical. Focusing technique is electronic. Convex. The image shape is blunt sector. Steering technique is electronic. Focusing technique is electronic. Vector. The image shape is trapezoidal. The steering technique is electronic. The focusing technique is electronic. Slice thickness or evaluation resolution. Resolution is accuracy in imaging. In addition to axial and lateral resolution, slice thickness or elevational resolution contributes to image quality. Image resolution actually deals with three-dimensional space, shallow to deep, side to side, and above to below imaging plane. Slice thickness is measured in a direction perpendicular to the imaging plane or above to below the imaging plane. We assume that the plane of our ultrasound image is razor thin. However, this assumption is not always correct. The beam has a measurable thickness that can vary with depth. When the slice is thick, structures above and beneath the assumed razor thin plane create reflections that appear in the image. Slice thickness resolution answers the following question. Are the reflections on the image created from structures directly in the imaging plane or from structures that lie above or beneath the imaging plane? Synonym. Slice thickness resolution is also called elevational resolution. More about elevational resolution. What shape of active element creates the best elevational resolution? Which transducer types have the best elevational resolution? Active elements that are disc-shaped provide the thinnest ultrasound slices and the best elevational resolution within the focal zone. Disc-shaped crystals are found in mechanical and annular phased array transducers. With disc-shaped crystals, the cross-section of a sound beam is a circle. The width of the circle in one direction indicates the beam diameter, determining lateral resolution, and the height of the circle indicates the beam thickness, determining elevational resolution. The elevational resolution is identical to the lateral resolution with disc-shaped active elements. What determines elevational resolution in phased array, linear array, and convex array transducers? These array probes have rectangular-shaped active elements placed side by side with phasing. The beam is focused or narrowed only side to side in the imaging plane, but not above and below. This narrowing improves lateral resolution, but does not affect slice thickness. With these array probes, an acoustic lens is used to create a thinner slice. Recall that lenses have a fixed focal depth. At the transducer, the beam thickness is equal to the height of the active element. At the focal depth, the beam thins to its minimal value. At greater depths, the beam thickens substantially. At all depths, the beam is much thicker than it is wide. Therefore, for these transducer styles, axial resolution is the best, followed by lateral and finally elevational. One limitation of linear arrays is the ability to dynamically create thin slices. What newer types of transducers have improved slice thickness resolution? Newer transducers, called 1-on-1 and 1/2 dimensional arrays, create thinner beams with improved slice thickness resolution over a great range of depths. The face of the 1.5D array transducer has numerous crystals arranged side by side. Unlike traditional linear phased and convex probes, which have a single crystal occupying each space, the 1.5D array has multiple crystals in the up and down direction. For example, the array might comprise 700 total elements, 100 wide by 7 high. Phasing, similar to that which improves lateral resolution, can be applied to the 7 vertical crystals, thereby thinning the slice and improving elevational resolution. Three-dimensional imaging. Three-dimensional, or 3D, or volume imaging is a recent innovation in ultrasound. A 2D array with thousands of elements arranged in a checkerboard pattern creates 3D images. With 2D array transducers, the sound beams are electronically focused in both a lateral and thickness planes. The beams are electronically steered, creating entire scan planes that sweep through anatomic structures. You may encounter the term 4D imaging. 4D is simply a trendy way of describing real-time 3D imaging. 4D imaging also uses 2D array probes. Rendering creates an image from three-dimensional data acquired during the ultrasound exam. It provides an element of realism to the image. Rendering constructs photo-like pictures with color, shadows, texture, and optical effects. Unlike regular photography, though, the images are computer-generated. This provides creative control over what appears in a rendered image. 3D rendering is often performed on an offline, standalone computer system after the ultrasound data has been acquired and stored. Under these conditions, 3D rendering is post-processing. An example of this technique is its use in creating classic 3D animated movies such as Lion King and Toy Story. Special topics. Side lobes. Sound beams created by single-element transducers are hourglass-shaped. However, additional areas of sound energy extend outside of the main beam in the far zone. These off-axis sound beams are called side lobes. Typically, the beam's main axis is much stronger than the side lobes. If, however, the lobes are of sufficient intensity, structures within them can generate reflections that create artifacts. Reflections arising from within the side lobes degrade lateral resolution. Grading lobes. Grading lobes are similar to side lobes, however, they are created by array transducers. Typically, the beam's main axis is much stronger than the grading lobes. These extra off-axis sound beams are undesirable because they degrade lateral resolution, reduce image quality, and create artifacts. Modern transducers are designed to reduce the strength of side and grading lobes. How is this accomplished? Since lobes can create artifacts, it is best to eliminate them. Reducing the strength of side and grading lobes can be achieved through a process called apodization. Figure 12.43 illustrates apodization. Imagine that 9 active elements of a linear array create a sound beam. When all 9 elements are excited by electrical spikes of similar voltage, grading lobes may be created. Grading lobes can be eliminated if the strength of the electrical spikes differs from element to element. In apodization, stronger electrical signals are used to excite the inner crystals, and progressively weaker electrical spikes excite the outer crystals. With apodization, lobes are diminished. Subdicing of each element in a linear array transducer also reduces grading lobes. With subdicing, a crystal is divided into a group of smaller crystals called subelements. These subelements are electrically joined and act as if they are a single crystal, which reduces grating loads. Modern transducers are designed to keep the sound beam narrow over a substantial depth range. How is this accomplished? A technique called dynamic aperture can be used to make a sound beam narrow over a greater range of depths and thus optimize lateral resolution. We have previously learned that transducer diameter in part determines beam width. The focus created by a small diameter active element is shallow, whereas the focus from a large diameter active element is deep. When an array transducer is used, the ultrasound system may change the number of crystals along the face of the probe used to transmit pulses and receive reflection. This process is called changing the aperture, variable aperture, or dynamic aperture. An aperture is an opening or a hole. The aperture may be thought of as the transmit hole or the listening hole. That is, the number of elements used to create sound beams or to receive reflected echoes. Dynamic aperture improves lateral resolution at a wide range of depths. Chapter 12 Review. True or false? Mechanical scanning produces pictures that are similar in shape to linear phased array images. That is true. Mechanical scanning and linear phased arrays create sector-shaped images. True or false? Many active elements fire at almost the same time in a mechanical scanner. False. There is only one active element in a mechanical scanner. True or false? Many active elements fire at almost the same time in a phased array scanner. True. Many active elements fire at almost the same time in a phased array scanner. Which of the following transducers is best described as mechanically steered and fixed single focus? An annular phased array, an annular array, a mechanical, or a linear phased? A mechanical transducer is the answer. C. A mechanical transducer steers the sound beam mechanically. The sound beam has a single fixed focus. Which of the following is best described as mechanically steered and multi-focus? Annular phased array transducer, annular sequential array transducer, a mechanical transducer, or a linear phased transducer? It would be an annular phased array transducer steer the sound beams mechanically. They are multi-focused. By the way, there is no such thing as an annular sequential array transducer. Which of the following transducers creates a rectangular shaped image? Annular phased array, linear sequential array, mechanical, or linear phased? It is B. A linear sequential array transducer is the only one of those choices that creates a rectangular shaped image. A linear phased array transducer has 128 crystals. How many of these crystals are fired to create a single sound beam? 1, a small group, a large group, or 128? The answer is D, 128. With linear phased array transducers, all of the active elements are fired to create each sound pulse. A linear sequential array transducer has 128 crystals. How many of these crystals are fired to create a single sound beam? 1, a small group, a large group, or 128? The answer is B, a small group. With linear sequential array transducers, a small group of active elements are fired to create each sound pulse. In a linear phased array, what is the firing pattern that steers a beam to the left or right? The firing pattern that steers a beam to the left or right is electronic slope. In linear phased arrays, What is the firing pattern that focuses a sound beam? The firing pattern that focuses a sound beam is electronic curvature. True or false? There are large time delays in the firing pattern of a linear phased array transducer. False. There are tiny time delays in the firing pattern of a linear phased array transducer. True or false? A machine that displays A mode in two-dimensional images is called a duplex scanner. False. A machine that displays Doppler in two-dimensional images is called a duplex scanner. Which of the following improves elevational resolution? A matrix array, a linear phased array, 1 1/2 dimensional array, or two-dimensional arrays? The answer is C. A 1 1/2 dimensional array transducer creates a thin slice and improves elevational resolution. True or false? Side lobes degrade axial resolution. False. True or false? Side lobes degrade lateral resolution. True.